In this video, we're going to draw what are called magnetic field lines. There are some similarities between electric field lines and magnetic ones. Whereas electric field lines would point from positive to negative, magnetic field lines will point from north to south. So one field line can leave a north pole of a magnet, make a loop, and then come back to the south pole. And we want to have an arrow showing the direction of the magnetic field. It's always going to be conventionally north to south. I'll make a couple of loops here. And that's great so far. Now, when it came to electric field lines, if you recall, I'll draw some on the side here. Electric field lines would point from a positive charge to a negative charge. And we could have lines that looked like this. But electric field lines were allowed to start and end on charges. If these point charges have an equal and opposite amount of charge on them, then the number of field lines leaving the positive should equal the number of field lines entering the negative. But one place where magnetic field lines differ from electric ones is that magnetic field lines cannot end. So they don't just start at a north and end on a south. They have to form complete loops. The direction of the magnetic field loop, though, is always consistent. Now, this may seem at first like a contradiction because field lines point from north to south, yet inside the magnet, it appears that they're pointing from south to north. But they aren't really pointing from south to north. Say we're able to break the magnet into two pieces. Magnets exhibit an interesting phenomenon that when they break, they can't be broken into single north or south poles. Whenever they break, a new north and a new south is created. And so the idea is that when we have our field line here, yes, it points from north to south on the outside, but on the inside, it doesn't point from south to north. It points from north to south if you assume that monopoles do not exist. The magnet can be broken in half over and over and over again, and it will always exhibit this phenomenon that there will be created a dipole. A dipole has both a north and a south in it. All right, so we can probably get one more field loop in here. That looks pretty good for the magnetic field around a bar magnet. If we're to draw the correct magnetic field lines in this situation, we have to assume that magnetic monopoles do not exist. This is fundamental to magnetism. So in these bar magnets, there would not be just a north alone. There must also be a south here and a north here. We want to draw the conventional direction of the magnetic field now. So we can have a loop leave the north here and come back through the south. Let's draw the complete loop though. And the field always points from north to south. That looks pretty good. What if we have a curved magnet? What will the field lines look like then? We still want our field lines to go from north to south, but magnets have an interesting property in that they can help direct the field lines. The material of the magnet itself helps propagate the field and control it. So we could have something that looks like this. Even Earth itself has a magnetic field. The Earth can be thought of as similar to a bar magnet, where one end is a south and the other end is a north. But which is which? The geographic North Pole is the top here, and the geographic South Pole is at the bottom. But is the top a north magnetic pole or a south? Well, a device which can help us answer this question is a compass. A compass is simply a magnetized needle which is fixed so that it's able to rotate and it can point toward a certain direction. One end of the needle tends to point toward geographic north. But just for context, let's remember what it was like for electric charges and how they were attracted to other charges. If we were to have a positive charge up here and a negative charge down here, and then let's say we've got in the middle here two particles attached to each other by a string. Let's say one of them is negative and the other is positive. This would be called an electric dipole. Which way would the dipole tend to rotate due to the electric field? Based on your experience with electrostatics, we know that negatives are attracted to positives, and positives are attracted to negatives. So we expect the dipole to rotate in such a way that the negative points toward the positive. What the dipole would do is it would want to align itself with the electric field. If we ignore the field created by the dipole itself, then we can see that the dipole would want to align itself with this external field, which I'll call E external. In this picture here, we see that it is very much aligned with the field. So a similar phenomenon will happen with magnetism. But in the old days, the needle which tended to point north was designated as a magnetic north. The other end, of course, was designated as a south. In the same way that negative charges are attracted to positive charges, magnetic norths are going to be attracted to magnetic souths. That means the pole which is at the top of the Earth here is actually a magnetic south. And the opposite pole is a magnetic north.